Foucault pendulum, proof of Earth rotation. What is a Foucault pendulum? Well, essentially it's a weight at the end of a string swinging back and forth. To illustrate the strange things that we notice with this, imagine going to the North Pole. Not here on this globe. Let's actually go to a playground and let a merry-go-round represent the top of the Earth. Imagine the white section there is all the ice at the top of the Earth in the North Pole and such, and the Earth is curving away. And we set up a pendulum at the North Pole. Well, this is pretty customary. As we look at this here, we set it in motion. Nothing out of the ordinary, nothing strange. It just simply swings back and forth. This would be our point of view if we were in outer space looking down on the Earth. But what if we go and rotate the Earth here? Now, the Earth happily rotating along, we would see something kind of interesting, sometimes strange to people, is that this pendulum doesn't change its plane of oscillation. It resists it. An object in motion tends to stay in motion. It has inertia. It doesn't want to change its plane of oscillation. So it stays steady, as long as you've corrected for any sort of friction and such. But what if we were to descend down and become a person on the planet looking at this, and we were to go and watch it? We see something kind of strange happening. We see that the plane of oscillation from our point of view, as a person riding along with the planet, seems to change. It seems to precess, it seems to change the direction of swing. But we know that that thing's trying to keep itself still, try to keep itself in the same plane of oscillation. Or maybe you think, oh, maybe there's some friction, we got something moving here or something like that. Well, if we step away from the merry-go-round, lo and behold, let's see what happens. It seems to be staying in its plane of oscillation quite happily. This seems to be what's going on with the Earth. Get rid of the merry-go-round. Let's just have a classroom and a weight and a string and set it in motion and let the Earth do the turning for us. Let the Earth turn the entire building. Let's look at a time lapse here. On this time lapse, we have the same weight oscillating back and forth, and it was co-aligned with this stick. When it started out, you can see the time zipping along there, but notice what happens. It begins to precess, it begins to rotate. The plane of oscillation begins to rotate to the right. In a qualitative sense, you can actually see this happening if you're patient enough. If you take a look at it from beneath, the direction of oscillation, or I should say the direction of precession, is reversed, but it's just from your point of view here. So on this, we can go and measure how many degrees per hour the Earth is rotating our location. Now, it would be ideal if you're at the North Pole, you would get about 15 degrees per hour. That's 360 degrees divided by 24 hours works out to 15 degrees per hour. But here, at about halfway down the side of the planet, roughly, we have about 11 degrees precession. But that can be measured. And as you head down to the equator, you eventually get to no precession whatsoever. There's no twisting of the buildings there. The buildings at the equator just roll over on themselves. You can imagine a building up at the North Pole. It doesn't roll, it twists. And we're measuring that twist with the Foucault pendulum. This was the first evidence, the first confirming evidence and measurements to show that the Earth was rotating and not the other way around, that the sun goes around the Earth or the stars go around the Earth. It helped get rid of the idea of the geocentric universe.